Okay, thank you for coming to my talk. So this slide is about myself and mainly about a new book I published. It's about statistical significance testing and limitations of statistical significance testing, how to compare your own system with existing systems using, statistical significance tests properly and things like that, how to design experiments. And I hope this will be of some use to you. So today's talk is based on this book, or actually the book is based on today's talk. So this today's talk is basically originally a SIGIR tutorial from last year, and I've been asked to do the same tutorial for the coming WASEDAM and also ECIR. So I'll be repeating mainly, primarily the same thing in different places. And today I will talk about, so my tutorial is basically a half day, so like 3 hours, but I will keep it like 1 hour. I will just focus on some of the main points in the second half of my tutorial because I assume that you know a lot about, you have, experience about, basics of significance testing and so on. Okay, so about myself, I'm from WASEDA대 University. I see a graduate here in this audience from my department, and I'm also a head of department and also a professor at NII, National Institute of Informatics, and so on. I also run this information retrieval journal, and this here we have Dr. Yong-In Song. We have a complicated relationship with him. We were mates. So I was at MSRA for 5 years, and at that time, Yong-In and I were colleagues. And later, when I became professor in 2013 at my university in Japan, he worked with me as a visiting researcher, and so we have been keeping in touch. And I have collaboration with Inokan's team. Yes, so basically I'm an information retrieval researcher, and today's topic is basically about, statistical significance testing, limitations, how to report properly, and so on, okay? Depending on your background knowledge, I can try to adjust my contents. If you think, the things that I mentioned are too boring for you, you can start yawning so I can speed up, okay? So this is the original SIGIR tutorial slide, and you can see that I'm starting with this, from the second part of the original tutorial. So the first part was mainly about how to do t-tests, how to do analysis of variance, but for now I assume that you know these things. Well, actually, I'm going to talk about one topic that's quite useful, which is the family-wise error rate. So probably you know all about this, but when I read papers from IR or NLP, some people do not do it right. So I will just, as a reminder, I will talk about what's wrong with doing t-tests many times, just repeating t-tests many times or ANOVA many times, or any significance test many times. So this is for people, those who are using R for significance testing. This is a very lazy method for doing t-tests many times. Suppose we have 3 systems. So we have 3 systems, and we are interested in the difference between every system pair. So we have 3 pairs. If you do this command in R, you can easily get a p-value for every combination, right? And this is, you probably know that this is not a right thing to do. So to discuss that, this is an analogy. This was made up by someone very clever several decades ago, I think. So what's wrong with doing, the same t-test this many times when M is the number of systems, okay? So this is the number of combinations, pairwise combinations you have given M systems. So why is it just wrong to do this many times? Okay, so this is you own a restaurant and you have a wine cellar, and you know that in every 20 bottles there is one sour wine. Okay, so if you pick up a bottle from your cellar, the probability that you pick up a sour wine is 5%. Now, if the customer comes to your restaurant and orders a bottle of wine, then the probability of serving him sour wine is obviously 5%. But I know that compared to Japanese people, Korean people are very good at drinking. So if you drink 2 bottles in a dinner, he orders 2 bottles, okay? Now, the probability of serving at least 1 sour bottle becomes 0.09, almost 10%. And obviously, you are not satisfied with 2 bottles. Maybe you order 3 bottles for your dinner. Now the probability is 14%. This is the probability of serving him at least 1 sour bottle of wine. And obviously, we do not want to do that. From the owner's point of view, you want to control the probability of serving sour wine to the customer. So that's the probability of serving sour wine, at least 1 sour bottle to a customer. You want to control that. So that should be, say, less than 5% if you decide on the number. Okay, and otherwise, this guy will tweet about your restaurant, and your restaurant will go bankrupt. So, as a researcher, it's the same. We have M systems, and instead of worrying about the error of each t-test, we should worry about the error of the entire set of tests for M systems, or this number of comparisons. So this is called the family-wise error rate, and we want to control this number, not this individual error rate. So this family-wise error rate should be, say, 5% or something, and then we can design experiments accordingly. Okay, so that's, this is obviously not my invention. People in statistics know about this, and they have several solutions. So the solutions are called multiple comparison procedures. If you have M systems and you want to control the family-wise error rate, there are several methods, but I'm going to talk about this very simple one because it's very simple and it works and it's very versatile. And you probably have heard of Bonferroni correction. You see this in many, even in recent papers, but this is actually considered obsolete in statistics. This is probably easy and better to use, Tukey's HSD test. So I will briefly discuss this one and also a computer-based, simpler version of this one for comparing M systems. So Bonferroni correction, this is, you don't have to read this. This is just a statement that Bonferroni correction is an old-fashioned way. And basically, it throws away many significant differences. So there are other better approaches. So this is called the Tukey HSD. If you know about this, it's boring for you, I'm sorry. But basically, this is like a t-test. The difference is that while the t-test controls the error rate for one test, this Tukey HSD test is similar to the t-test, but it controls the family-wise error rate. Given M systems, you are interested in every system pair, and you want to control the family-wise error rate. You want to set it to, say, 5% or below. So to do that, we use this some strange function called the studentized range distribution instead of the t-distribution. How this works is actually not that difficult. So if you have M systems, then you have this combination of system pairs, right? So you have this number of different between system differences. Among these differences, there are large differences, there are small differences, but this test pays attention to the largest difference among these comparisons, okay? Now, the difference is a random variable, and therefore the maximum value among these different differences are also a random variable. So this distribution is actually exactly the distribution that this random variable obeys, the maximum value among the k differences obey. That's this studentized range distribution. So what we're doing is consider the worst case. We have different, large differences, small differences, but we pay attention to the largest difference, and we look at the distribution of that largest difference, okay? And we ensure that, just like the t-test, the error rate for that is 5%, okay? Then that means if the largest difference is not statistically significant, then the other differences are automatically not statistically significant. So in this way, they ensure 5% error rate for the entire set. If you understand this kind of logic, then after that, it's just easy for you to apply these tests. These are just basic stuff. So for example, this is an unpaired data situation. You have M systems, you have N observations for each system, but there is no direct relationship between these values. So you happen to have N observations for system 1, N observations for system 2, but these are not related. So this is the unpaired data situation. And this is how you compute the test statistic. This is very similar to the t-test, and the only difference is that we use this new distribution, but the principle is the same as the t-test. And this is how you do the actual test in R. You do some kind of analysis of variance function here, and then you use the Tukey HSD function, and automatically R will give you the proper p-value for every system pair. And these are the confidence intervals. So this is the right way. This is better than doing t-tests many times, as I said, because it ensures that the family-wise error rate is 5%, not the individual error rate. And this can be applied to paired data. This is the usual situation when we have a test collection and we compare M systems using N topics, for example. Now we have paired data. So this is a matrix, and we have a similar method to compute the test statistic and then obtain the p-value. This time, because now we have paired data, this part looks different, but if you just follow the code, you can just do the Tukey HSD test. And by the way, so as I said, these are called confidence intervals, but these are actually simultaneous confidence intervals, which means if you do a t-test and compute a confidence interval, you ensure 95% confidence for this one, but not for this one, not for this one. You don't care about the other ones. But here we are trying to simultaneously capture the correct difference between systems. Anyway, so I will skip this confidence interval part, but that's what this means. So if you are interested, you can have a look at my book. So if you thought using R is, involves lots of equations and assumptions, mathematical assumptions, if you don't like assumptions, you can try this version as well. This uses computational power, but it's free from distributional assumptions like the basic normality, random sampling assumption, and so on. So I will give you a different approach to doing the same thing as the Tukey HSD test. So there are, in contrast to classical significance testing that uses, relies on assumptions like normality, equal variance, random sampling. There are several assumptions they use so that they can come up with a mathematically well-formed formulas for distributions. But these ones use the computational power to draw a distribution to use for significance testing. So they are quite not entirely assumption-free, but nearly assumption-free. So I'm going to talk about this one, the randomization test and the Tukey HSD version of that. So this is for comparing two tests. So you can use this test instead of the t-test if you like, because the t-test assumes normality and random sampling assumption. So now you have two systems, okay? You have, and it's paired data. You compared maybe, so this is Naver, this is Google, and you used n queries to compare Naver's search result and Google's search result. So this is the mean NDCG for Naver, mean NDCG for Google, okay? And there is a difference in the observed data, but you want to know, is this difference actual? Are they really different? So in contrast to a classical significance testing, let's assume this, let's set up this null hypothesis. It says, so there's a hidden system, okay? This hidden system generates NDCG scores. For each query, it produces 2 NDCG scores. It's the same system. And it flips a coin, and if it's head, it gives the score to Naver. If it's tail, it gives it to Google. So this assignment is completely random. Okay, let's assume that. So that assumption means basically these values are actually equivalent because they come from the same system, not Google versus Naver. They are actually a single system, so there should be no difference. So that's the assumption. Now, if the assumption is correct, then instead of this, we could have had these variants as well, right? So these are obtained by swapping, each row at random. So, for example, here we have Naver's score, Google score, instead of Google score, Naver score. So we create these permutations, and you can figure out how many possible matrices we can have, right? But computing lots of these is computationally too expensive because it's exponential. So let's just do, let's say, 10,000 trials, okay? So if this was true, instead of having this, maybe we could have had these as well, because the coin flipping should be random. Now, for these variants, from these variants, let's obtain the difference between Naver and Google. Okay, so this is the difference obtained from this matrix. This is the difference obtained from this matrix. Okay, now we draw a histogram of these values. We get a histogram like this, and this is exactly the null hypothesis distribution, right? So the null hypothesis was that, okay, all these numbers come from the same system. Under that assumption, we could have had these. Therefore, under this assumption, then this is the likely distribution. Okay, so this is a probability density function. So, if you actually compute the observed difference from your actual matrix, this is the actual difference, right? And if this observed value is something very extreme compared to this distribution, then you start doubting your null hypothesis, right? Okay, if this is true, then the distribution of the differences should be something like this. But what I've seen from my data is something much, much smaller, much more extreme than this distribution. Therefore, since this value is very unlikely, let's reject this hypothesis. That's the logic. Okay, so pseudocode, so this is the actual clumsily implemented code, but you can try for yourself. This works. So, for example, it's a shell script. This is a list of system names. This is the actual score matrix, and the trial number is 5,000. After maybe a few hours, we can obtain a p-value. So you can see that instead of doing the t-test with several assumptions, we just use the computational power to draw a distribution and then do significance testing. Now we can extend that to paired Tukey HSD situation where we have more than 2 systems. So I think since you are bright people at Naver, I'm sure you can understand, the logic applies to more than 2 systems, right? We have, I don't know, Naver, Baidu, Google, or something, okay? And we want to test whether these, if Naver is better than Google, if Naver is better than Baidu, if Baidu is better than Google. We are interested in every combination, okay? So we assume that, okay, all of these 3 numbers come from the same system, just like before. So what we do, it's easy. You permute all these rows like this. We create, randomly shuffle each row to obtain these variants. Okay. Now, please remember what we did with the Tukey HSD test. What we did was, although we had k different comparisons, we paid attention to the maximum difference among the k comparisons, right? So what you can do is, for each of the variant matrix, we take the smallest value and the largest value to obtain the maximum difference among the k comparisons. So this is the maximum difference from this matrix. This is the maximum difference from this matrix. We draw the distribution of the maximum difference. Okay. Now, from the observed matrix, we have three different between system differences: x1 minus x2, x2 minus x3, x1 minus x3. So we compare these observed values against the distribution of the largest difference. So this is exactly what the Tukey's Q distribution was trying to draw. Okay. Now the logic is, you can see the logic. So among these three, this is the largest difference, right? And if this is not statistically significant, then the smaller differences, these are not statistically significant either. So in this way, the principle of Tukey HSD applies. So again, if we set alpha to 5%, we can say the family-wise error rate for the entire comparisons is 5%. Okay, so the tool can be used in the same way. Now we have three systems in this list, and that's why we get three different p-values. Okay. Okay, so that's something practical for comparing more than two systems. And probably you are interested in limitations of significance testing and what we can do about it, and also how to design experiments, properly, how to decide on the scale of the experiment. So I have some insights about it, so I will discuss that with you. So you don't have to read these. The point is that since, even from the 60s, there has been criticisms on statistical significance testing. I'm talking about statistical significance. I wrote a book about significance testing, but from the 60s or maybe earlier, people have been criticizing this approach. This guy is saying it's actually harming research in psychological, I guess. This guy from 75, this guy is talking about even teaching. He's saying we should stop teaching significance testing in class, okay, because it's rubbish. So in psychology and medicine, they use lots of significance testing, and they are complaining about it. This is meaningless. That's what he's saying. And Cohen, you probably heard of, right? Cohen is very big. He was a very famous statistician, and even Cohen is saying this is rubbish. So null hypothesis significance testing means you set alpha to 5% and say whether significant or not. That's called NHST, or null hypothesis significance testing, and he calls it SHIT. He really thinks it's rubbish. Okay, and this is also Cohen. This is a more concrete criticism. He says, we researchers or developers, we want to know, given these data, what is the probability that my hypothesis is true? This is what we really want to know. But if you know what p-value is, this is not this green probability, right? The p-value is this probability. So the probability of the data or something more extreme given the null hypothesis. That's the p-value. But we are more, this is more straightforward, right? This is like, okay, we have the data. What's the probability of my hypothesis is true? But these are not equivalent, obviously. And so I'm running this information retrieval journal, but this is a journal where a journal editor tried to ban significance testing. Okay? The journal editor said, do not do significance testing. Otherwise, we will reject your paper. Okay? So the researchers in this domain started avoiding significant testing, but after the editor stepped down and was replaced by another editor, they started using significant testing again. Okay? So it's like, you know, like a disease in a way. So lots of criticisms. There's also a concrete criticism. So we often talk about whether something is statistically significant or not. Okay? If it's significant, maybe we can submit a paper to SIGIR or Wisdom or your favorite conference, www. If it's not significant, then okay, we cannot publish a paper. And that idea is called the dichotomous decision or binary decision. Okay? Significant or not significant. So I'm going to summarize three major issues in classical significant testing. One issue, the first issue is that many people misinterpret or misuse classical significant tests and misunderstand p-values and confidence intervals and so on. If you read the right textbooks, it should be clear, but p-values, a p-value is this, right? Given the hypothesis, what's the probability of the data or something more extreme? So this H is the null hypothesis, and this is not this probability. But this was a statement from the American Statistical Association in 2016. They had to say, okay, p-values are not these probabilities, which means basically nobody understands the right definition, right? So first thing is, it's difficult to understand, it's not straightforward, and many people misuse significance testing. But there are at least two more problems. This is the second one. Like I said, many people think about whether your result is statistically significant or not. If it's significant, you can publish a paper. If not, you cannot publish a paper, you cannot graduate, and so on. But it's really silly, right? If this is your p-value, it's not statistically significant at 5%, so you cannot write your PhD thesis, you cannot graduate. If you have this number, now you can graduate. Okay, this is not the way it should be, right? So in papers, you often see stars or asterisks. A star meaning significant. Lack of star meaning not significant, but this is a very bad practice. You should report the exact p-value, okay? This is more informative. But this is not enough. This is the third point. So the problem with this p-value is that it's a function of these two things, okay? A p-value is a function of the effect size, and what's an effect size? Effect size just means how much difference there is. How much difference, not whether there is a difference. How much difference there is. Magnitude of the difference, okay? So that's the effect size. So we want a large effect, okay? But unfortunately, p-value is also a function of the sample size. For example, let's think about the t-test. This is what we compute for the t-test. If the t is large, then p is small, so we get a statistically significant difference. But if you see this blue part is actually the effect size. So if you look at the meaning, so this is the mean difference, right? And this is a standard deviation. So the blue part means how much is the difference if measured in standard deviation units. How many standard deviation units is the difference between Google and Naver? Okay, so this is very important. Now, but you can see that there is this red part, and n is the sample size. Okay, number of topics, number of queries. So this means if you increase the sample size, then you can increase t, therefore you can make p arbitrarily small. So if you want to publish a paper with a statistical significance, you can have a very large sample, you can get a significant difference, maybe you can get in. Your paper may get in at a conference, but that's not really right. It's not right science, yeah? So, the bottom line is, when you write a paper, what needs to be done is to report not only the p-value, but also this blue part, the effect size. Because now that way you can separate the effect of the actual magnitude of the difference and the sample size. Okay, I have some examples later. So I see I've talked about for about 30 minutes. I think I'm doing fine. So I will talk a little more about effect sizes and statistical power. These are several different definitions of effect size. By the way, the slide deck is available from SlideShare. You can search for my name and SIGIR tutorial. You can find it. I will probably revise the slides for Wisdom and ECIR, but the basic contents will be the same. Okay, so for example, for t-test, like I said, this is an effect size you can report. This is the actual difference divided by a standard deviation. So this form of effect size is called standardized mean difference. And there are several other variants, but basically it's the same. So this is the difference between population means, this is the population standard deviation, and we are trying to estimate this population effect size in several different ways. So I will skip the details, but so the point is reporting the p-value, the actual p-value, and the effect size will be good. You know, if you want to do good research, if you want to report results properly so that other people can repeat your experiments or reproduce your experiments, these practices should be introduced in our communities. So I'm going to talk a little bit about statistical power. So if you know significance testing, you probably know that there's this probability of type 1 error. There's also the probability of type 2 error, and so on. Let's just do a revision, quick revision of this contingency table. Okay, so these two rows represent two different worlds. We live in either this world or this world, right? So that our null hypothesis is true, or our null hypothesis is false. It's either this world or this world. Now, as for the columns, they represent our decisions after doing an experiment. So here in this cell, the null hypothesis is true. The systems are equivalent, and we fail to reject H0. So we say the systems are not statistically significantly different. So this is a correct conclusion. Whereas if we reject H0, even though the systems are equivalent, then that's a type 1 error. We say the systems are different even though they are not. So this is a type 1 error. So we have the other error, which is in the population. If you look at the population means, the systems are actually different. Naver is actually better than Google. But in your experiment, you fail to reach that conclusion. You say the difference between Google and Naver is not statistically significant. You are, missing the real difference. So that's the type 2 error. Now we have this cell which says, okay, the actual systems are different, and we correctly conclude that Naver is better than Google. So this is also a correct conclusion. And this probability, 1 minus beta, is called the statistical power. So you know that statistical power means the ability to detect a real difference, right? And there are interactions between 4 things. Alpha, we can decide like 5%, 1%, 10%, right? Beta is harder to control, but we want it to be, for example, 20% if this is 5%, or this could be 5% as well. We want to control this. But these are determined based on the other 2 factors. One is the sample size, n, and the other is the effect size. So we have alpha, beta, effect size, sample size. And if we decide on the 3, then the 4th one is automatically determined. And what's dangerous about doing experiments and doing significance testing is that there are overpowered experiments and underpowered experiments. Okay, in companies like yours, I think you can easily have overpowered experiments. You have lots of data, you have lots of queries, so usually you have in your experiments you have a lot more data than necessary to reach a conclusion. This is actually not a bad thing because you're rich. You already have the data, so it's okay to use lots of data. But please be warned that, as I mentioned, if this is much larger than necessary, then you are diminishing the p-value, right? So anything can be statistically significant. You are obtaining statistical significance too easily, and your actual effect size might be very small. So that can happen for overpowered experiments. And for poor academics like me, although I worked for industry for 20 years, now I'm a poor academic, right? I need to collaborate with you guys to get, rich data. For university professors, we do this all the time. Underpowered experiments, especially for user experiments. For example, we hire 20 students from my lab and do a user experiment, which system is better. But usually this number is too small, which means this probability is too small. Even if there is a difference between two systems, then we will miss that difference most of the time. I will give you some examples from SIGIR. Okay. I'm not going to go into details of these, but just maybe some history will interest you. So you recognize this person, Karen Spark-Jones. Karen Spark-Jones was the inventor of IDF, inverse document frequency, from the Cambridge Computer Lab. She died in 2007, I think. She was my supervisor at Cambridge. She designed a test collection in 1975. She tried to design a test collection, and this was her consideration of the number of topics or queries. Okay, she said, okay, if we have less than 75 topics or queries, oh, that's no real value. We should have at least 250. Maybe for some purposes we need more than 1,000. That was 1975, okay? Because she wanted statistically significant results and so on. And curiously, you know what happened at TREC, right? TREC, Text Retrieval Conference, started in 1992, and the American people at NIST, National Institute of Standards and Technology, they decided to have test collections with 50 topics, right? And so that became a de facto standard, 50 topics per experiment. And obviously that's much smaller than what Karen envisioned in the 70s, right? But this became the standard practice. But, for example, in 2009, Ellen Voorhees, who runs TREC, did some experiments and concluded this is not enough. And I think she's right. So there are several ways to decide on the number of queries or the sample size based on statistical considerations. So, for example, my Excel tools can decide on the number of topics for our test collection using based on the statistical power of the t-test or ANOVA, or the width of the confidence interval between two systems. I will skip the details, but the Excel tools are available online. So what for example, what you can do is you set the type 1 error probability to say 5%. You set beta to say 20%. And you say, okay, probably in my experiments I'll be comparing maybe 10 systems, and you set this number called the minimal detectable range. So we want 80% power, but when you say power, you need to think about the actual difference, because when you are discussing power, that means there is a difference between different systems, and in the case of ANOVA, we have M systems, so this D is the largest difference among the K comparisons. And when you say I want 80% power or 20% beta, you need to say I want 80% power whenever the actual difference between the best and the worst system is, say, 0.1 or maybe larger. Okay. And this is a variance estimate you need for a particular evaluation measure like NDCG. So you need to enter these numbers, but if you enter these numbers, then my Excel tool will automatically give you the right sample size. So you need 312 topics if you want this condition. and this is for a particular evaluation measure. So basically the main message is if you have a statistical requirement, you can design a test collection accordingly. Lots of too many equations. This is just a slide that reminds you that different evaluation measures have different variances. NDCG, you probably know. This is the variance you get from track data for NDCG. If you look at ERR, expected reciprocal rank, this is an evaluation measure suitable for navigational queries. You can see that this is much more unstable. Okay? If you use an unstable measure, then you need a larger topic set size. Also, I will briefly discuss what you can, how you can read a paper and then discuss the power of that experiment. So my tools written in R, actually I stole the code from WASEDA professor, and I hacked the code to make it easier for us to understand. So given a SIGIR paper, okay, we can compute the effect size from the experiment and the actual power in that experiment. And then we can redesign the experiment. We can propose a new sample size to achieve, say, 80% power. I will skip the details. I will just give you some examples from SIGIR, okay? So all you have to enter are, for example, all you have to enter are these values. The t value from the t-test, the sample size, and you get these numbers. This is the effect size from the experiment. This is the achieved power, 15% power, which is really bad. Do you see what this means? This means even if you have a existing true difference, you're going to miss the difference in your conclusion 85% of the time. So this is basically a waste of time because this is the sample size is too small. The sample size is 28. If you wanted 80% power, actually they should have used 244 topics, not 28. So these things is actually quite useful. If you are interested in doing an experiment, you can read a similar experiment in an existing study and then look at these numbers and then consider how many topics you are going to need or maybe how many users you should employ. So this is from my SIGIR 2016 paper. Back then, I had some time to do these things. I read over 1,000 papers from SIGIR and TOEIS from a decade, okay? And I looked at what kind of significance tests are used. Some people do not use significant tests. Some people do not report what significant test they used. And for these papers, I was able to analyze that power thing because they are good papers. They reported the right statistics, like the t statistic, sample size, or something from the analysis of variance. And for these ones, I could use the R tool to obtain, the actual statistical power. And some of them are highly underpowered. Some of them are highly overpowered. So this is a graph. This is an overview of 75 SIGIR papers with a paired t-test or unpaired t-test. So this number on the y-axis is called the sample size ratio. It's the required sample size. The actual sample size divided by the required sample size for 80% power. So, for example, this dot means a SIGIR paper where only actually 5 topics was necessary, but in the experiment they used 192. So this is a highly overpowered experiment, which is okay, but you should really report the effect size to separate the effect of the sample size and the effect size in the p-value. So if you look at this part, you've already seen this example actually. So the paper used 28 topics, but actually they needed 244 topics to do 80% power. Okay, so these are real problems in IR and probably with other disciplines too. Okay, I want to leave some time for questions and discussions, so I'll try to finish within like 3 minutes or so. So to conclude, when you write a paper, to write a good paper, you should report your sample size and you should say mean NDCG or mean average precision or whatever, and you can report the t statistic, the degrees of freedom, the actual p-value, confidence interval, and the effect size, like this. This is for unpaired data, similar here. I will skip this part. Even when you're doing, two-key HSD for comparing more than two systems, you can report the p-value of each comparison and also the effect size, where the effect size is given like this. So it's the actual difference divided by a standard deviation obtained in some way. To report that in a paper, you need to include lots of details, but maybe you can just cite my book when you do this. Okay? So to sum up, I talked about significance testing. I'm sure you understand the basic principle of significance testing. I reminded you about the family-wise error rate problem as opposed to the comparison-wise error rate. We need to care about comparing M systems, doing K comparisons, and to try to control the family-wise error rate. And one approach is to do the two-key HSD test or do a randomized version of the two-key HSD test. And if you are designing a data set, then you can consider statistical power. There are ways to do it. We shouldn't be creating 50 topics just because Trek does that. Okay? And when you report your results, please report as many details as possible, the p-values, not just the stars, effect sizes, degrees of freedom, and so on. So other researchers and developers can reproduce your experiments. I'm not sure if you're aware that ACM started this reproducibility badge thing. From now on, if there is a SIGIR paper that looks like the results can be reproduced, they will give that paper a kind of a badge saying, okay, this paper is completely reproducible or replicable, and so on. So if you are interested in these evaluation of IR systems, web search, and so on, this book came out this month, and I hope you will enjoy this book. And thank you for listening. That's it from me.
Can I ask you a question?
Yeah.
Is there any researches focusing on the query side, like sampling topic queries?
I'm sure there are. Yongi asked a similar question, but I'm not familiar with those things because these approaches, they basically assume random sampling. So if you manipulate data, that kind of violates the basic assumption. So, but I think I agree that that's an important avenue for research, but I'm not really familiar with the techniques.
Another question. Actually, I'm familiar with the recommendation system, so I'm wondering if there is any statistical experiment for the recommendation scenarios. For example, sampling users or number of users is sufficient, something like that. Is also relevant to your research.
Yes. So basically, this is not really, not really research. It's just statistics. But as long as you have something similar to my data structure, in my example, it was queries versus systems, but it could be different product items versus users. It could be different matrices, and depending on the number of the size of the data, the variance of your entire data set will, vary. And depending on the variance, then, we need to determine what is the right size of your recommendation experiment. So yes, this is, this says IR, but it's many of these stuff is applicable to NLP recommendation and other things.
Thank you.